Oh, then we got more. I guess I threw this one on the end after. All right. This clearly looked like it was supposed to be the last page, but we got more. All right. So I think this was the last time I taught this course. I put a question on the exam, and you know what they did? They bombed it. So what do I do when people bomb things? I fry into my pretzels and I make PowerPoint slides. In fact, I've added these PowerPoint slides to my 3101 class, right? So with them, we go over we don't do the pointers very fast, but we do we skip the pointers kind of, but the loop invariant part is good. All right? All right, so maybe we should put this on the exam. All right, so here's the problem. And all of these things, these white things, are cut out of the exam itself. All right? So, and I would say you don't have to read all the text because the picture is perfect, right? What's the precondition of the problem? You have this circular linked list, right? It goes around in a circle, and you have a pointer which is pointing at the last one, right? Everybody got the loop invariant? All right, and if you know Jesus, he says, whoever's last shall be first, right? So what we're going to do is we're going to turn every pointer to go in the other direction, all right? So last is still pointing in the same place, but everyone is turned around, right? Everybody get what we're doing? All right. Then I said, what's our loop invariant? And I didn't make people come up with it themselves. I gave it, but it kind of makes sense that, or maybe I made them come up with themselves. Some of this might be answer, I don't know. But after you've iterated twice, say, what does each iteration do, right? We're going to kind of turn them around one at a time. So after you've iterated twice, we've turned two of them around, right? And so what should it look like? Well, it should look like this, right? Two of them have turned around and everything else is kind of the same. Right? Everybody good? Anybody have a problem with this picture? You should. There's a problem with this picture. Yes. Yeah, the middle picture. Yeah. Right? Nobody is pointing at these guys, right? So we need pointers, right? And what do I call them? This one's called done because it's pointing at the ones that are done. And this one's to do is pointing at the ones that are done already, to be done, right? And if you're a little smart and you look at this picture just so, what do we have here? It's two stacks, right? Done is pointing at a linked list. To do is pointing at a linked list. What do we want to do? We want to take one that we need to do and pop it off the stack and push it on the other stack, right? All right. All right, so then you want to draw a picture. We only need to maintain this loop invariant. All right, so here's the picture after two iterations. So you draw the picture after three iterations, and then we have a whole lesson on how to point, how to do these. Why? Because I threw it over to 3101. But people need a reminder of this? Right? Oh, so here we go. Right? So now we can see, right, what's happening here. right? Which values change and what's their new value, right? So the key is that 3 has to point over there, right? And done has to move and to do has to move, right? So right, who has that? Who, right? This is done is the value that 3 is, right? So where's done? It's over there. So who has it over there? So what's the code? We say done. Done now points where to do is pointing, right? Everybody good with that? All right, we did it. Now what also happens? Right, it's just again explaining what's happening there, right? What else changes? To do changes, right? Where's to do supposed to point? To do supposed to point at the 4, right? Who has it? The 3 has it, right? So basically, what are we doing here? We write the code. To do is walking forward, right? Everybody see that? To do is walking. All right, what else do we have to do? It's a classic walking move. All right, what else values changes? That value changes, right? Where does it change, right? It needs to point over at 2, right? So who's pointing at it, right? Done is pointing at it. So we can just say to do dot next points where done is pointing, right? Are people being able to do these codes? Right? Everybody good with these 3 code? So we have to, yeah. Yes, that's what I was about to say. Exactly. All right, so we've changed 3. In fact, what we have is we have 3 numbers and we've rotated them 1, right? So each is fine in itself, but you can't do them all at the same time, right? What order do we do these things in? And we can't, right? So those are a great 3 lines, but what order do you do them in, right? Doesn't matter. In whichever order you do them in, somebody gets dropped, right? So one option is to have 1 value and then swap them around. If you're really lazy, you have 3 temporary values, right? Everybody good? Oh yeah, here's a bug, right? So here, to do is changed. So you have to make sure that it's the right old to do, right? So that's where I'm kind of throwing here. You got to keep track of the old values versus the new values, right? It's a little tricky to get it all right. And keeping track of what's the old value and the new value is useful. All right, is everybody following along? We're whipping through this material. Right? Fewer lines, right? We can bring in a temp. And, right? Yeah. Well, even with 2 things, if I have these 2 things and want to swap them, I need 2 hands, right? If I pick this one up, I can't put it there, right? So, right, but if you pick up one, you can move the other and move the other, and then put this one down. Yeah. Right? I mean, how am I going to swap these? Well, even you're doing this, right? You need to pick this one up into a temporary value, right? Then you move this one over and you put this one down. Yeah. I think figures, the drawings are really great, and the code is what Jackie's going to want, right? I'm going to want the pictures. He's going to want the code. So, and in this case, for example, instead of making people read all that words, I gave most of the pictures. I don't know which pictures I didn't give, right? Did I give the loop invariant picture? I did. It might have been a question of draw me the loop invariant picture, right? Draw me at time 2, and then draw it for me at time 3, and then give me the code that goes from the 2-1 to the 3-1, right? So certainly, I would say even in life, if you have this problem, you want to think, what's my loop invariant, right? Draw the picture at some time 2, and then draw the picture at some time 3, and then write the code to move from the 2 to the 3, and then to see if that same code moves you all along, right? And then think about what does roll the time backwards to say, what's the loop invariant at time 0, right? And how do I establish that? And then from that, does my same code move forward, right? I guess that's my religion I'm trying to push on you, is that pictures are good. Everybody good? Right? I mean, which you like better, text like this or a picture? Right? I don't know. To me, pictures are pretty good. All right. All right. So, this is, again, let's roll it back. And what's the precondition, right? So here's kind of time 1, right, where you've done one of them. Oops. And then you roll it back. All right, well, I don't know where the time 0 is, but you can roll it back to times, and yeah, well, it's not there, so let's not worry about it. And then, here's time 0. I knew there was time 0, right? If you roll it back far enough, then nothing's done, right? And then you want to think, where's to do and done pointing, right? And to do is pointing at the first one to do, and done is pointing at whoever's been done already, but that's nobody. So does it need to point at anything? And then you can ask, here's a question, can done, this is a very good question, guy. Can I have done pointing at last? Yeah. Yeah. Well, last is pointing here. But it's not done because we're going from the front of the list. Yeah. Well, you can, because you got last, right? We could have done point at 6 if you wanted to. But my question is, can you point it at this box last? Right? Right? So I can have an arrow to here. Can I have an arrow to here? No. Why? No. It's a type question issue, right? Done is of type pointer to a node. And that's not a node. So you can't point at it, right? If you were in C, you could point at it. But in Java, you can't point at it. All right? So where are we going to have done point? I think it can point at nowhere. That's fine, right? Where should done point? Oh, here is my question. Can it point there? No, it's the wrong type, right? Last is of type pointer to node. So if you pointed at it, you would be of type pointer to node, right? None of the nodes are done, so let's just have it point to nil. Right, everybody good? So how do you set up the code? To do, there you go, to do equals last next, right? And we don't care about done at all, right? We could set the value to nil, or we could just have it do whatever it's doing. All right. And then if you get, you should always make sure that your first iteration works, right? So this was our code, and we're going from here, right? You run it, and you see, you run it if it works. And wanted to point at 6. Oh yeah. So yeah. So I take it back. I was thinking that done didn't need to point anywhere, right? But 6 is where 1's supposed to point, and so the code needs done pointing at 6, right? Everybody kind of. That's why you run the code and see what happens. All right. Right. So there we go. We fixed the code. Now. So now we want to keep going until we're ready to stop, right? You keep running it until they've all been rotated, right? Here, right? They've all been turned around. Oh, so if you keep going, that's what it's going to look like, right? To do last is going to, done is pointing at who's done. And you think about where to do is going to go. It's going to keep coming. It's going to go somewhere, right? And so you have to test when you're done, right? And we won't get into it, but the bottom line is the solution set I handed out didn't have, was it would stop, but it would never start. And the problem with is when it couldn't, when it was pointing the right direction, my exit condition would stop and not start. So you needed to change things. And let's not go into it. Yeah.
Write our code in a way where we can make it work and take one step and meet our loop invariant, then we're pretty much good. So we just have to figure out the loop invariant.
Yeah. All you have to do, what's the goal here? You have a pitch. Let's review what you need to do. You have a picture of the precondition. You draw a picture of the postcondition. You draw a picture of the loop invariant somewhere in the middle. You draw a picture one step later, right? You give the code of how to move one step, right? Then you take the loop invariant and you wind it back to 0 iterations, right? And you have code to get from the precondition picture to that first loop invariant, right? To establish the loop invariant. And then if this initial loop invariant picture is a little weird, you run the code to see if it works, right? That first step. And then you run it until you've done all the iterations. What does the loop invariant look like? How do you get from that picture to the postcondition, right? How do you know when to stop, right? So I would say, right, is this, I mean, you can tell me what you think. Is this problem too hard for a test, right? If you know all of those steps, right, none of the steps were that hard, right? The hardest one was the rotation of the 3 things, right? But when I said the students didn't do well at it, I'm not saying there was a little bug in their various people's programs. I'm saying, 20% got it perfect, right? Half of them muddled around, and half of them did nothing, right? So you have to, people good? Yep. I don't know, it'd be a different picture. It would change everything a little bit. Yeah, I don't know. It would change the beginning and the end. I just made this up. And that's it for these slides. All right? How are people doing with assertions and loop invariants? You think you can do it? Right? What do we got? What are the key things we've done? Talked about pointers. The recursion was thrown in there. Do you know? I'm gonna, I asked, do you guys understand recursive backtracking? I mean, if that knapsack problem is sort of your classic recursive backtracking, and my code tells you how to modify it to a couple of sort of scenarios. And I'm not making up the coding test, but if I were, it's going to be what was on the practice test. There was one question where you had one friend, and then there were 3 questions where you did recursive backtracking, right? Now, on the test, I don't know, can he give you 2 problems to do? Probably not. If he gives you 1, what is it going to be? It's going to be a modification of that recursive backtracking, right? So I would say flip through my slides, and if you don't really get it, then we should talk about it at some point. Yeah? What? No, I meant the practice test was what you did last night. Yeah, the assignment, right? It was, I think it's only worth 5%. If you hand in poetry, you would get full marks, right? I think, right? So I call that a practice test, right? Right, so then there's going to be a lab test, right? And that's what you want to be ready for, right? And then there's one, sort of the more theory parts, right? There's a theory test that I give you and a theory test that everybody gives you, right? If I was making a theory question right now, what would it be on it? Something about loop invariants, something about pointers, right? It's kind of asking for that one we just did, right? Something about recursion, I suppose, right? That's what we've done so far. Any questions about those topics? Well, I think I haven't taught this course that many times, and I think the things that I've done have been worked into the slides. But if you really want practice, you can go to 3101, my 3101 slides, because they have a million examples in the slides and the videos and the practice questions and yeah, lots and lots and lots. The danger of going there, however, is that they're harder than we're doing here. In fact, the problem with my practice questions at 3101 is they're too hard for the students, because what happens is I've been teaching for a long, long time, and the difficulty of the tests has gotten easier and easier and easier over the times, right? So those practice ones were from previous pass-through assignments and they're harder, right? Any other thoughts?
Hello, excuse me, Professor.
Yes,
So you just mentioned your 3101 practice.
yes.
I'm thinking about maybe starting that. So the content will be similar. If I practice for 3101, then I should be able to be on a better footing for 2101. Is that correct?
But I didn't quite catch the question, but 3101 is here and it has a big thing on loop invariance and a big thing on recursion.
All right, great. So my question was that the content was similar. So practicing the 3101 would help me with 2101. Is that
Yeah,
correct?
except it might be too hard.
All right. I'll take a challenge. Thank you.
Yeah, yeah. I mean, you can, if you go here, loop invariance, right? These are all videos. It always makes me nervous when it says that. I mean, it was in progress before, right? Did you have a question? Thought? Yeah, yeah. In fact, in dynamic programming, right? We've already done one little greedy algorithm, right? When we did, right? And then dynamic programming, one of the first examples is knapsack problem, right? And all right, so let's go back to this dot. And we're now doing running time. In fact, let's dates. Today is the 29th. All right, so I've been talking too fast, guys. You haven't been asking enough questions, right? So feel free to ask questions. That's what the bottom line is. All right, so what are we doing here? We're doing running time.